Okay. Should be recording. We're off to the races. So like we said, we'll try to finish up sets this week so that we'll be done with chapter 2, and then we'll move into chapter 12. Remember, we're going to jump around quite a bit in the textbook, so but I looked ahead and it has a nice flow, so works for me. All right, so just as a brief review, because it was just on Monday, I'm not going to spend a lot of time reviewing, but we'll just kind of talk about what we said last week or last day, and then start with an example that we didn't get to last day. So for review, right, we talked about sets and properties of sets and their properties. And then we started talking about the fundamental set operations. Fundamental set operations, which are the intersection, the union, and the complement. The intersection, right? That's when we use the cap, or you can read it as and. The union, which is the U, right? Or the cup, if you prefer, which you can read as or. And then the complement, oops. Which was just kind of a, say, a bar, which is the opposite of the set A, right? So the complement is everything that's not in A, for example, if that's the set you're talking about. And so we started talking about those, showing those in Venn diagrams, and then I didn't have enough time to go through an example, so we'll start there and just kind of, I'll indicate the end of the review, and then we'll start with an example from last day. If we let the universal set, now remember we use the capital U again, by context it'll be very clear whether it means the union or the universal set, right? And so that shouldn't be an issue. Oh, yeah, so in the assignments, you should be able to do the assignment as many times as you want until you have the grade that you want. Hopefully those are the settings. I'll have to go through and check them, but if it's not letting you do that, let me know. And oh, there's a cap. What, do you know what the cap is, Ashley? Okay. I will go in and change how many attempts, because I want you guys to just kind of have at it, right? Okay. So I'll have to, before I forget, I'll just make a note. Attempts in web assigned, just so I go in and make sure that you have as many as you know, is reasonable, probably 10 or so for, if you need more than 10, talk to me and we can make it happen. Okay, so if we let the universal set just be the counting numbers 1 through 9, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. Hey, a rare instance where my right curly bracket looks better than my left. Thank you. Thank you. Thank you. Thank you. We'll let A be the set of 2, 4, 6, and 8. And let B be the set 1, 3, 5, and 7. And C is going to be the set of just 5 and 7. Okay. So I want you to find the following: A union C, B union C, B intersection C, or I just kind of do B and C, or say B and C, and then A and C. So just take a quick moment, and I'll start drawing out this this Venn diagram here. But I want you guys to have a little try. Remembering that the U is or, right? So it can be in either of the sets or both. And then the cap is and, so it has to be in both of the sets. And a Venn diagram is usually pretty helpful. Okay. So here, I don't think we talked about this, so I just want to mention, when you're drawing your Venn diagram, so here we're talking about, oh, and I forgot, U has 9. When you're drawing your Venn diagram and you see that you have a universal set, so that's your big rectangle, and then you've got 3 other sets, just go ahead and draw circles. So they don't, you can just leave spaces empty if there's nothing in them. So you don't have to try to kind of adjust your circles so that there's no overlap, in case in this situation there isn't any overlap in A and C, for example, right? Or even A and B. So, right, so you don't have to adjust it, you can just show it with nothing in it, right? Because it's more of a visualization tool. So if we want to be in A or C, right, then all the items in, or the elements in A, 2, 4, 6, 8 would be in there, but also in C, which is 5 and 7. So in going in order here, 2, 4, 6, and then C has 5. I should do that. Do them in order, otherwise it gets 5, 6, and 7, and 8. Oh. Usually I have to do a scrap one and then arrange them nicely. Because you want to have them in order, otherwise it can be easy to miss one. But sometimes it's just easier to put A and then C, and then just C, sort them out later. But trying to be fancy here. So if it can be in either B or C, well, in B there's 1, 3, 5, and 7, and then in C there's. Sorry, say that again.
Sorry, I didn't know my mic was.
Oh. Awesome. So in B, we've got 1, 3, 5, and 7, and then in C, we've got 5 and 7 again. So really, in B or C, we've just got 1, 3, 5, and 7. If you've drawn your Venn diagram, right, then you see that B and C is just the set of 5 and 7. Oops. And then either by looking at A and C, you'll see that there's no overlap, but also in the Venn diagram, right, there are no elements in the A and C area shared. And so what we say is we have the empty set, right? Or if you prefer, your empty brackets, if you're typing. So let's talk about, we'll brush up on our cardinalities. Cardinalities aren't that bad, right? It's just the number of elements inside a set. And so we can talk about the cardinalities of all these things. Remember, we just indicate them with the 2 vertical bars, just like an absolute value sign, right? And so if we have cardinalities, well, the cardinality of A, well, I guess I'll do U first, is just 9. Cardinality of A is 1, 2, 3, 4, same with B. And the cardinality of C is just 2. So if we just have a look, right, our unions and our intersections, we can figure out what the cardinalities of these things are. So if we have listed them, then it's pretty easy, right? So if we want the cardinality of A or C, well, that's going to be 1, 2, 3, 4, 5, 6. If we want B or C, well, that was just 1, 2, 3, 4. And then the cardinality of B and C was 2. And the cardinality of A and C was 0, right? And just as a reminder that since the cardinality of the empty set is 0. Okay. So what you can kind of see is that, okay, so if we've got the union, right, the cardinality gets a little bit trickier, right, because it could be in A or B, whereas the intersection, it's pretty cut and dry, right? And so when we're talking about the cardinalities of unions, we have to kind of pay more attention because there could be that dual overlap. Okay. So the cardinality of a union, we'll say, requires more attention than intersections. Okay, and we'll see why in a little bit. But you can probably see just from the Venn diagram. It requires more attention than intersections. Yeah. So just as a reminder, right, we've got the cardinality of B, we said was 4, and the cardinality of C was 2. But then we also said that the cardinality of B I should say B or C, was still just 4, right? Because C is inside B. And if we want to talk about subsets, right, C is a proper subset of B because it's contained, all the elements are contained in B and it's not equal to B. We'll start flexing all our terminology. Okay. So we can have this pop up, and so there are rules for these things. And so what we do is we take the cardinality of the first set, the cardinality of the second set, but then we have to subtract the overlap once, right? And then you'll be kind of on an even plane again. So in general, for any sets X and Y, the cardinality of X or Y, or union Y, is the cardinality of X plus the cardinality of Y minus the cardinality of X and Y. Here, right, we have to subtract the overlap. So that's what's going on there, is we'll have that overlap and we need to deal with that. So if we do a little example, some of these examples in the beginning at least take more time to write out than they do solving, but that's okay. So I've shorthanded them. Of course, there should be a blurb, but you're living in a city and you want to know how many teachers or homeowners there are, so that you can either be counting teachers or homeowners, or there are some teachers who are also homeowners, right? And so we want to count how many there are, right? So how many teachers or homeowners? If there are 50,000 teachers, jokes, homeowners. Although I could do that and it really wouldn't matter. Just be a tougher sell for you guys. 50,000 homeowners and 4,000 teachers. But then, of course, there's 3,000 teachers who own their own home. Who own their own home. So with a little bit of notation, right? So we'll get better at kind of denoting our sets and saying, let H be the homeowners and let T be the teachers. But for now, I'm just going to say that we're going to denote the homeowners with an H and the teachers with a T, right? So the set H and the set T. And so what we want to find, right, is the cardinality, right? The number of elements inside H or T, right? Or T or H, it doesn't matter the order. Homeowners or teachers or both, right? How many are there? So we've got the cardinality of H plus the cardinality of T minus the overlap, which is H and T. Oops. Round bracket out of nowhere. Teachers who own their own home, right? That's going to be H and T. So now we just go 50,000 plus 4,000 minus 3,000, putting us at 51,000 teachers or homeowners. Nice. We'll amp it up in the next section here. Any questions before we get into 2.3? So far, so good. Put it on a fresh page here. So 2.3 is more about the applications of sets. Now we're going to talk about just kind of combining operations, right? So not just A or B, we can talk about A or B and C, that kind of thing, so we can have combined operations. And so we'll start with combined operations with sets. Right. Just like we can have lots of different algebraic things going on, we can do the same thing with sets. One thing that is really kind of not so cut and dry, to me at least, is that we do all these operations from left to right, but sometimes, to me, looking back, it's not obvious why, and I'll show you an example here. But it's just going to be a matter of seeing enough of these things and knowing the order of operations, right? Just like BEDMAS, if you're doing straight math, right, we need to follow BEDMAS, and so here we just read from left to right, and that's our BEDMAS for sets. So we read left to right. Unless there are brackets. In that case, of course, we deal with the brackets first because that's what they're saying. We read left to right unless there are brackets. Which are solved. I'll put solved in air quotes here, which are solved first, right? Or kind of handled first. So as a quick example, so the complement of A or the complement of B. If we had to look at this thing, right, and figure out what parts of the set this is, right, because this is going to yield a new set. So what we can do is we can draw the Venn diagram to try to figure out what set this is, right, the complement of A or the complement of B. So when we read left to right, first thing we come across is the complement of A. Right. So first, we'll have the complement of A, and it gets kind of tricky. So maybe multiple colors work or different line types will work, right? Because we're kind of working through these as layers. So the complement of A is everything not in A, right? And so just for now, I'll do that to say that, okay, the complement of A, that's done. And then I want or the complement of B, which means that I'm going to have to find the complement of B and then do the or operation on it. Right? And so the complement of B, let's pick kind of a light color. Well, the complement of B is just everything that's not in B. Hard to see maybe. Anyways. And if I want A or B, or sorry, the complement of A or the complement of B, right? Any area that's been shaded, that's applied, right? And so, whereas if I had the complement of A and the complement of B, right, then it would be only the areas that have been shaded twice. Okay? So in our case, the whole thing I'll shade in pink, right? So it's anything that's been touched by color, which is just everything except for that midsection there. Not very clear. But that's what we're doing here. We'll even be able to use Venn diagrams as proofs. So we'll see a brief little proof later of De Morgan's laws, but for now, right? Because if we end up with two Venn diagrams that look exactly the same, then the two sets are the same. Right? If we have a look at A or B, the complement of A or B, right, it's going to be slightly different. Okay? Because now, if I read this from left to right, and here's where I kind of, well, that's not obvious to me that it should be the complement of, so first I have to find A or B, and then I have to find the complement of it, and that's what I'm looking for, right? And so, to me, looking back, it's not obvious, but you just kind of develop this gut feeling of, okay, first I have to find A or B, and then I want the complement, right? And so, or if it makes sense to you, then you're ahead of me. Or ahead of where I was, I guess, before, in my undergrad. So if we've got A or B, right, we're talking about A or B, that's everything in the circles, in the overlap, as well as the two outer circles. And so the complement of that is a little bit easier to wrap our heads around. It's just going to be everything outside the circles. So here, in a way, we've proven, right? So this shows that the complement of A or the complement of B, right, is not going to be the same as the complement of A or B, right? So we can't just split those up. They don't behave that way, right? And so we have rules for that, of course, and that's where De Morgan's laws come in, and De Morgan's laws are going to be kind of a big player for sets. So here we go. De Morgan's laws. De Morgan's law says that, and there are two rules or two laws, just for two sets X and Y, X union Y bar, or sometimes I say not, right? It's just the opposite. Trying to say complement and be proper, but so the complement of X union Y is the same, so it will be equivalent to the complement of X and the complement of y, right? So something happens in there and we'll check it out, but just as like a little memory thing, the u becomes a cap, right, when you split them up. And then vice versa is the other law that we have. So we have x and y bar is equal to x bar union y bar. Oops. And I'll kind of wrap these up in some sort of highlighter here. We can show that this is true using Venn diagrams, right? So we'll prove it. Do a little proof. Do you guys have to take proofs, a proofs course? No. Time will tell, right? Proofs they're fun. They're can be a little bit tricky, but pretty fun. So let's see here. What if we want to show that, oops, the first law, x union y all bar, is x bar and y bar. So if you start by drawing out the two Venn diagrams, if they end up looking the same in the end, then there's your proof, right? So that's all we need to do for these little proofs, is just show the Venn diagram on the one side is equal to the Venn diagram on the other side. Draw Venn diagrams to show they are equal. I feel like we just did that, but may as well do it again. So if we have, x or y, the complement of x or y, and then giving myself a lot of space here, x bar and y bar. So we know what the Venn diagram of x or y bar looks like. So I've got x or y, that's everything in the circles. And so the complement of that is just going to be everything on the outside. I wish there was like and maybe there is, maybe I just don't know about it, like one of those paint buckets, really, really old school, where it's like, fill it with green, done. Maybe there is something worth looking for when you're working with sets. So that one's easy. The first one's easy. The second one is a little bit trickier. And take a couple more steps to draw out. Oh yeah. Yeah, the problem is if you don't close off your Venn diagram properly. So if you're too sloppy. All of mine are probably open. Yeah, they are. The whole page would get colored. Okay, so we want not X, so the complement of X. What color should I use here? So everything that's not X is going to be orange. Kind of have to keep yourself accountable here. Keep track of what you've drawn in if you're sloppy like me. No, you guys aren't sloppy like me. And then not Y. So first I'm going to do not Y, which is everything not in Y. And then I want the intersection of the two, which is only where things have been colored in twice, I should say, right? Because it has to be not X and not Y. And so, let's see here. I'll do a dark color, although I did purple already. Eek. The areas colored in twice is all that, right? These two Venn diagrams would be the same, right? Once we kind of clean this up. We would have two Venn diagrams that are the same. Since the Venn diagrams are the same, QED, yeah, exactly. We have proved that X union Y bar equals X bar and Y bar. Okay, how would you describe the XU bar, X bar, and Y bar is? So I would say it's the complement of X or Y. No problem. NP. Okay. So just a little proof. But something to have up your sleeve. All right, let's get into more than two sets. We've already seen just briefly in that example A, B, and C, right? But now let's talk about 3 or potentially even more sets. So if we have 3 sets, for 3 sets, our Venn diagram, just in general, is always going to look like this. And again, if there's no elements in the shared areas, then you just leave it blank, right? So you don't have to remove the overlap or anything. That'd be crazy. So we're just going to have A, B, or C. Is that like a hazmat symbol? Hazardous materials. 3 sets. Okay. So if this is our general biohazard, hey, that makes more sense. Hazmat. It's like a hazmat suit. I guess that's what I was thinking of. Anyways, looks nasty. If I asked you to shade in, so now we're going to talk about more than 2 sets here. And so I want you to shade, shade A or, and then in brackets B and C, right? So we read from left to right and we apply these things left to right, but if there's brackets, then you have to deal with the brackets first and then move out. Let you do that while I draw up my Venn diagram here. So first, you're going to have to deal with the B and C. Right? And so B and C becomes kind of its own unit. And so what we've got here is we've got B and C, which is just the overlap between B and C. And then we can take that area and look at A or that area, right? And so we're going to look at A or that shaded area. So everything in A applies as well. And that's the area that we're looking for. So that would be a new set. What if I wanted you to shade A or B, so the complement of that, so the complement of A or B and C. I'll get to work drawing my Venn diagram here. Hey, what am I doing? I should have just been copying and pasting my first one. Oh. So let's see what we've got here. So first I'm going to deal with the complement of A or B, right? Reading from left to right, but also that's a package deal. So A or B, and then its complement is just everything outside A or B. Then I have to tack on the and C. So it also has to be in C. So the only thing that applies here is, so here, this is the area that we want. Well, maybe the highlighter just kind of does a better job. There. That would be the area that we would want.
Emily?
Yes?
So for something like this where we have to shade this area, would you expect to see the orange shading in the outside as well as the double in C, or just what's got the most overlap?
Yeah, so your end result would just be the one with the most overlap in this case, because we want A or B, so the complement of A or B. So the whole set, my final answer should actually look like just the, oh, not like that. It should just look like this. But I'm just being sloppy and not doing it twice.
Okay, thanks.
Venn diagram, Venn diagram. Yeah, so So your final answer should just be the set that it's talking about. But I'm just being lazy. Did I do? Yeah, okay. So let's see here. So those, I think, once you do a few and you kind of see how they work, then they're not so bad. Just as a rule, so the union operation is associative, so it doesn't matter, just like addition, A plus B plus C, it doesn't matter if you put brackets around A and B or B and C, it'll all just stay the same, right? So the union works the same way. And so just as another LFF, little fun fact, the union operation is associative, meaning that P or Q brackets or R is the same as P, oops, should say union. P union bracket Q union R bracket. Pure. Pure equals pure. Yeah. So that's just what it means to be associative. Oh, an LFF is a little fun fact. Little and fun, exactly. Exactly. The best kinds of facts are little and fun. Yeah, little, fun. Would it be a little intersection? Anyways. I always tell my stats crew that that Venn diagrams are usually just really good for jokes. A lot of good jokes in Venn diagrams. If you're dealing with 3 sets, or you could have even more than 3 sets, a Venn diagram for 5 sets looks really cool, but also really wonky. It like kind of makes ovals to make, anyways, we're not going that far, we're sticking to 3. But if we're talking about the cardinalities, right, coming back to what we were talking about before, where we were talking about the number of elements in these resulting sets, it can be really tricky. So a lot of the time, we're just, if we're dealing with 3 or more sets, just do the Venn diagram and just count, right? So don't worry about any formulas or anything like that. Like we had De Morgan's laws for 2 sets, and there are laws and rules and formulas for more than 2 sets, but my advice to you is just use the Venn diagram and count. Okay? Not very fancy, but it works. And usually way quicker. So to find the cardinality, of a combination of 3 or more sets, we will use the Venn diagram. We will use a Venn diagram to count the number of elements. To count the number of elements. So the Venn diagram is pretty self-explanatory if you've just got two sets, but now we've got three sets or potentially more. So as just kind of to put some structure into it, when you're drawing your Venn diagrams, always start in the middle. So start in the section with the most overlap and put that value in there, and then just kind of bloom out into the rest of your Venn diagram, right? Keeping in mind that that intersection, those have already been counted, so you would remove those as you move out. Okay? And then when you're finished, you should go back and make sure that you have everything in the universal set. So if there's supposed to be 50 elements, for example, just go through and quickly count to make sure that all 50 of them are there. Okay? So, oops. When drawing your Venn diagram, always start in the middle. Always start I'm sure it's not my pen, but I feel like my pen keeps glitching. I'm trying to not hold my pen so hard because my hand really cramps up, but here I am. Iron grip. So when drawing your Venn diagram, always start in the middle. And work your way out. And then finish by counting all the areas to make sure that you have the whole universal set. And then finish by counting all areas to make sure you have the entire universal set. Yeah. For example, let's say we have 100 randomly selected students and they're all taking some set of courses, right? And so we'll draw a Venn diagram and just solve some word problems using the Venn diagram. So if we have 100 randomly selected students, uh, 100 randomly selected students gave the following information. Maybe I should put it all on the same page for later. 45 of them are taking math. Do you guys, I hope it's okay that I just write math. I think, or I'll write it for the first one and not the rest, are taking math. 41 are taking English. 40 are taking history. 15 are taking math and English. 18 are taking math and history. 17 are taking English and history. And 7 are taking all three. So just as an exercise before we get started with just finding some specific information, first, let's develop some notation, right? So the most common, right, we use capital letters. I'm going to use M for math, E for English, H for history. Seems reasonable, right? And so I'm just going to define that here. Usually we would say let M and then be the set of students taking math. Okay, all right. I'll be proper math. Let M be the set of students taking math. E English, H history. Here I'll get lazy. English. So then, these counts that we've been given, they're cardinalities, right? So they're the number of elements in the set. How many students are in the set of students taking math? Well, so the cardinality of M, we're told, is 45. The cardinality of E, we're told, is 41. And the cardinality of H is 40. We've got a couple of other little tidbits, right? We know the cardinality of M and E, right? Math and English is 15. So M and E is 15. The cardinality of math and history is 18. And the cardinality of English and history is 17. And finally, the cardinality of math and English and history, we're told is 7. So that's just to kind of get to thinking about these things in terms of cardinalities, but also in terms of sets, right? So we can break it down to the most basic of the sets, and then we'll have combinations, right? Because at least in the past when I've taught this kind of stuff, people want to make another set for math and English and a separate set for math and history, separate set for English and history, but you don't need to do that, right? You just need to look at the 3 core sets and then do combinations, which in turn are their own sets, but they're just combined sets. So, how many are taking only math, right? So here, I'll write out some of the questions that we're going to answer, and then we'll use a Venn diagram to answer them. Okay. How many are taking only math? Only English, only history, or not taking any of these courses.
Question?
Yeah.
When it says math and English or math and history, does that and mean an intersection or a union?
It means the intersection. So it has to be in math and English, for example. So, so it's only that little sliver that they share.
Or is that how it, okay, so we're supposed to be conditioning our minds for the and being an intersection. Okay.
So I'll start drawing our Venn diagram here. So like I said, you'll want to start in the middle and then bloom out for your counts. You know what? What the hey? It's not even real paper, so I'm going to make it nice and big here. It's fake paper. Don't waste the pixels. I know. Hashtag save the pixels. It's true. Yeah. I'll do math, English, and history. Okay. And then of course out here, I've got my universal set, which is just all students, right? So, like I said, we're gonna start in the middle, and what I'm gonna do is I'm just gonna put the counts in each of the regions, right? And so we know the one with the most overlap is all the students in math, English, and history. So I'm gonna put a 7 there. Maybe I'll do a different color so it's easier to read. 7. So then blooming out, right, I can move to, let's say, this intersection here, right, math and history, but I've already got a 7 in there. So the math and history has a count of 18, right? But I've already got 7 of them on the board, and so the ones out here are going to be 11, right? Because 11 and 7 make that total 18. Okay? Same idea if I go to, let's say, English and history, right, to fill this space here. English and history had 17. I've already managed to take care of 7. So there's 10 in that overlapping space. Same idea. Math and English have this intersection here. I've already got 7 of them. Math and English have 15, putting me at 8. I don't do math. I always have my calculator. Well, just kind of a funny story, because by the end of my undergrad, I was doing 1 + 1 in my calculator just to be sure. So anyways, kind of ruins you. Everyone's like, oh, so you did a math degree, cool. So you must be really good at like math in your head. No, not at all, actually opposite. Anyways, you'll see. Move on to this region here. So now I've taken, so here, now I'm in trouble. I've taken care of 8 and 7 and 11, right? And so I have to subtract that from my whole M, right? And so from M, I've got 45, safe now, right? I've got 45, but I have to take away 8, take away 7, and take away 11. 19. Which answers the first question, right? The first question was, how many are taking only math, right? So only math, that's this whole region, right? Everything in the M circle, but nothing in the overlap, right? And so the answer is 19. Right. So I'll put that here. Taking only English, well, we need to know how many are in the English circle. There's 41. So same thing, maybe I should show. Equals 41 minus 8 minus 7 minus 10. So 41 minus 8 minus 7 minus 10, putting you at 16. Yeah. So there are 16 students only taking English. Well, of the 3 courses, I guess. Same thing, only history. History was 40. 40 minus 11 minus 7 minus 10. I have to deal with the outside rectangle, right? There's a chance that there are students who aren't taking any of these courses, which would be the answer to the last question. So here, this was 12, right? And so what I have to do is I have to go through and I have to add these all up. And so I've got 19 plus 8 plus 7 plus 11. And you could do fancy stuff, but I would not recommend it. Like you could do the whole math circle, the whole English circle, and the whole history circle, and then subtract the overlaps, but I wouldn't. Right. So I'm just gonna straight add them up. I've got 19, 8, 7, 11, plus 16, plus 10, plus 12, hopefully I got them all, 83. So 100 minus 83. So there's 17 students who aren't taking any of those 3 courses. They're taking other courses, right? This wasn't the universal set of courses, right? So that's what I mean by, and then of course, just to double check, you would run through and add all those numbers up again, just to make sure that you reach 100, which is where our total sample size was. But I'm gonna assume that they do. So like I said, when you're drawing these Venn diagrams, you're gonna start in the center and kind of bloom your way out. Okay. Last section of sets. Last section of sets. Let's see here. Put it on a fresh page here. So section 2.4 is going to talk about finite and infinite sets. Hey, that's weird. Why don't we say infinite? Say finite and infinite. Something to think about. Finite and infinite, infinite. Just English things. I know. It's how when I finally realized that definitely is just definitely, then I was able to spell it. So definitely, that's definitely. finite and infinite sets. Okay. So there are some sets, right? Like the counting numbers, we know we could count forever, right? So we call them infinite sets, right? Because they just keep going and going and going and going. We run into some troubles because infinity is not a number, it's more of a state of mind. No, it's more of an idea, right? And so infinity can't be used as a number, so we have to deal with that. But we can have infinite sets. And so the set of natural numbers, so our counting numbers, 1, 2, 3, 4, 5, 6, 7, the set of integers, they're all infinite sets. Okay. So certain sets, such as the set of natural numbers, and the set of integers, are infinite sets. Because they keep going and going and going and going and going. And then of course, if we're able to if there is an end to a set, right, regardless of how large, if it is theoretically countable, then we call it a finite set. Okay? So even if a cardinality is 0, then we would still call it a finite set, of course, because definitely countable if it's empty. So if the cardinality of a set is 0, or a counting number the set is finite. Even if we don't know its exact cardinality. Even if we don't know its exact cardinality. Most things are going to be finite, right? Anything that we kind of talk about that isn't the set of integers or the set of natural numbers, they're just going to be finite sets. So even if, I think there was an example about the number of drops of water on Earth, can't count them, right? We can approximate them, and therefore it's still a finite set, right? Because the argument being, well, you could contain the whole Earth in some container, figure out how much that container would be, and then there is an end to that, right? And so even though for us it's kind of hard to think about, we still say that that's a finite set because it can be done, even though we don't know what the cardinality of the number of drops of water on Earth are. It can be done, right? So therefore it's a finite set. Okay? So we talked about equivalent sets, right? Equivalent sets just have the same number of elements, right? So they have the same cardinality. And we use equivalent sets and cardinalities when we count things. So just, I'm counting 1, 2, 3 cars outside, right? Technically what I'm doing is I'm using a 1-to-1 correspondence. So I'm taking the first car and I'm matching it with the counting number 1 in the set of natural numbers, right? And then I'm looking at the second car and I'm giving it the number 2, and I'm matching it to the number 2 in the set of natural numbers. So this idea of matching elements in a set is called one-to-one correspondence. It's really hot in here. It's like the first sunny day in a long time here, but anyways. So we should enjoy it, but it's really hot. Yeah, let me write that down. Whenever we count something, we are using the idea of, aren't you in Edmonton? Shouldn't it be snowing? Probably. Yesterday I was convinced it was gonna snow. It was so cold, but here now it's a balmy 19 degrees. Crazy, right? So whenever we count something, we are using the idea of cardinality and equivalent sets. Right. By, I'll say pairing. Oops. By pairing, whoa, it turned it into a nice arrow. Okay, it's not what I wanted, but pretty cool. By pairing the items being counted, right, with an element from the natural numbers. By pairing the element being counted with an element from the set of natural numbers. Uh-oh. Here comes my dog. She's mad. A lot of activity today. One-to-one correspondence is what we call that. When we're matching an element that we're counting to another element in the natural numbers, or even going from one set to another, we can have one-to-one correspondence when we're able to match from one set to another set, meaning they must have the same cardinality because there can't be any left over, right? And so one-to-one correspondence just means that two sets have the same cardinality, and that's it. Two sets, A and B, are said to be in one-to-one correspondence, or in a one-to-one correspondence if we can find a pairing, that first, each element of A is paired with precisely one element, so that's what makes it one-to-one, precisely one element of B, and then similarly one element in B matches precisely with one element in A. So each element of A is paired with precisely one element of B and ditto for B to A. So each element of B is paired with precisely is paired with precisely one element of A. Because this is kind of an important definition, it is pretty kind of self-explanatory, right? I'm gonna put a little box around it. Okay. So this can only happen if two sets have the same cardinality, right? Because if the cardinality of B is larger than the cardinality of A, there's going to be some left over in B that can't get matched to anything in A, and so you can't have a one-to-one correspondence. So if two sets A and B, or X and Y, or whatever, have the same cardinality, they can be placed into a one-to-one correspondence. They can be placed into a one-to-one correspondence. Okay. So we write A is equivalent to B, right? That was the notation that we used to have the same cardinality, right? A and B are equivalent to each other if they have the same cardinality. But we also use this to indicate that it's a one-to-one correspondence. To indicate a one-to-one correspondence. Bet you didn't know we do. Well, I learned about one Hebrew letter, Aleph. So I didn't actually know. I don't remember seeing this notation ever. Doesn't mean I didn't see it though, but I just don't remember. So it's obviously not a big player in a lot of math, but maybe for on the computer science. Can we use a triple equal sign for equivalency? I don't know. I don't know if that's, is that what you're doing in other courses? Yeah? Okay. Well, now that you've said it, I'll know. Yeah. 1 minus 1. Yeah, if you want to do a triple equal sign, that's fine. I'll know what you mean. Yeah, is exactly the same as, so it's not actually equal. I would probably just stick to the double-sided arrow just to be safe, because I need to brush up on my set notation. But yeah, so I don't want to say yes and then have it be wrong. But, so let's just stick to the double-sided arrow. And yeah, definitely you can use some sort of shorthand for one-to-one. 1 minus 1 works. Or 121, 1-to-1. Oh yeah, so why do we need this aleph? The Hebrew letter aleph. It's to indicate the cardinality of infinite sets. Because like I said, the problem is that, okay, infinity is not a number, it's more of an idea, right? And so we can't use infinity as the cardinality, but we do need some way to indicate that, hey, the cardinality of this thing is just massive, right? So it's infinite, there's no number for it. Okay? And so to indicate, and there's all these little cute historical notes about Cantor who came up with this notation in the textbook, but I'll leave that to the reader. So to indicate the cardinality, of the counting numbers, so the set of natural numbers, right, the set of natural numbers, we use the Hebrew letter. So in math, you get really good at Greek letters. My first Hebrew letter. Aleph, or if you prefer with the PH, they seem to be interchangeable. With a subscript 0, okay. Oh, I'll just follow it up with, since infinity is not a number. Okay. So Aleph, how we're gonna draw it, and I'll show you what it actually looks like unless you've already looked it up, but it looks like this. So you draw a diagonal line, and then over here you draw a little curved guy, and then another little curved guy up above, and then the subscript 0. And this is called Aleph naught. Typically, a subscript 0, we call it naught. Naught, null, 0, they're all the same. Right? So Aleph looks like this. I had to figure out how to, because I was like, I can't draw that, right? Just this fancy curve. It's got a little foot on it. Anyways, so we're just doing a very basic Aleph, okay? So Aleph is only for the cardinality, right? The number of elements in in an infinite set. Okay. So, yeah, the calligraphy set would come in handy here. And maybe there's like a calligraphy, there's an app for that, I'm sure of it. Yeah, it's like, I don't know, it's got all these components. It's like branching. It's beautiful, but I cannot draw it. So I looked up how it was okay to draw it by hand, and this was it. So this is Aleph Knot. And so we're talking about infinite sets, right? And so N with aspirations, exactly. Yeah, no, it's an N ready to party. So, we already said that, okay, the definition of Aleph Knot is it's the cardinality of the natural number set. Okay, so the cardinality of the set of natural numbers, and I should make it clear that it's the set of natural numbers, is this Aleph Knot. It'll change every time, I think. Okay. So if we consider the set of natural numbers, well, that's the set of 1, 2, 3, 4. Taking a break, at some point we'll hit some number n, and then it just keeps going infinitely, right? And so this is the set of natural numbers. We can also introduce the set E. E, let's call it the set of even numbers, right? And so the set of even numbers, 2, 4, 6, 8, da da da. And then instead of n, it's 2n, da 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 da. Here's the thing. Even though E is contained in the set of natural numbers, because it's infinite, it's also going to have the cardinality of Aleph Knot. Okay? So that's a little bit weird, right? Because what you end up having is the set of even numbers has a cardinality of Aleph Knot, and then the set of odd numbers has a cardinality of Aleph Knot, but then those two combined make up the set N, which also has a cardinality of Aleph Knot. And so that, for me, that's a little bit hard to wrap my head around, because it looks like Aleph Knot plus Aleph Knot equals Aleph Knot. Are you sick of me saying Aleph Knot yet? Aleph Knot, I'll stop. Didn't really work. But so that's important, right? That's the whole idea with these infinite sets is, well, infinity, we can't really wrap our heads around it, right? And so if we do kind of an infinite set plus an infinite set, well, it yields an infinite set, right? So that's the whole idea with the Aleph Knots again. So I'm going to scoot this over so that I can put the cardinalities just beside here. So the cardinality of the set N of natural numbers is, here we go, boop, boop, boop. Yeah. A little flair to it. And the cardinality of E is also Aleph Knot. Okay. You'll also see, right, that we can, because we've got an infinite ways to go, right? Because these are infinite sets, we're actually able to map these to each other. And we're able to establish this one-to-one correspondence. Now that's weird to think about, right? But we can, right? So there's this one-to-one correspondence in there. So a lot of this is just kind of like, but it is. So they have the same cardinality of Aleph Not, right? But also E is a subset of the set of natural numbers, right? And it's a proper subset because it's not the natural numbers, right? It's contained in there. And so what we end up with is, we call this, so this is by definition an infinite set. And so we can think about infinite sets and decide, well, is it finite or infinite? But by definition, an infinite set is something with a proper subset. Oh yeah, I'll write it down. But an infinite set is a set that can be placed into a one-to-one correspondence with a proper subset of itself, right? So when we have this type of scenario here, right, when we can put, so question mark. Oh, nice. Yes. Yeah. How'd you get that double arrow? So fancy. Pretty cool.
The shift of the forward slash.
Say that again.
When you press shift forward slash.
Oh, cool. Things I did not know. Awesome. Yes. Okay. I was writing a note here. So since all elements of E, are elements in the set of natural numbers, are elements in the set of natural numbers n, and E is not equal to the set of natural numbers, right? Because there are components of the natural numbers that aren't in E. We know E is a proper subset of n. We know E is a proper subset of n. Oops. So we'll do the definition of infinite sets, which is just a summary of what we just showed. And what I read out to you earlier. An infinite set is a set that can be placed into a one-to-one correspondence, is a set that can be placed into a one-to-one correspondence with a proper subset of itself. Oops. With a proper subset of itself. And because it's a proper definition, put a little box around it, I think. So we're going to talk about kind of countable, but not that much. If a set is finite, of course it's countable, but even if it has cardinality aleph naught, we still say that it's countable. Right? We're just never going to get there, right? But countable. Okay? So if a set is finite or has cardinality, cardinality aleph naught, we say the set is countable. And there are a few sets that are not countable. The set of real numbers is not countable. In fact, the set, even between the set of numbers between 1 and 2 is not countable, because you can go to infinitely many decimal places, and so not countable. Right, so if you're on the real number line, so as soon as you're involving a number line, it's no longer countable, right? Even between 0.1 and 0.2, still not countable, because we can go as deep into the decimals as we want, right? Or don't want to, depends. So the set of real numbers of real numbers, capital R, double back, is not countable. Oops. Any interval on the real number line is not countable. Right? Because it just depends on the number of decimal places that you want to go to. I think it was the same guy, Cantor, but memory kind of fails me now, who decided that, okay, the cardinality of the set of real numbers is going to be a lowercase c. I'll put it down here, but we're not going to use it. So instead of aleph naught, just use a lowercase c. You could also use aleph 1, but I guess that's still a field of research, because they're still trying to figure out if there are any sets with cardinalities between the set of real numbers or the set of natural numbers and the set of real numbers. Anyways, kind of, they're still working on that, trying to figure out if there are any sets. There might be, and I guess there are sets with higher orders of aleph, but obviously we're not going down that route. So, but just kind of fun to know. They're working on it. Stay tuned. No, it's going to take years. Way too long. And we probably won't even know about it on the news when they do, but it'll be kind of a big deal. Okay. I just have one thing, but I think because I'm running out of time, I'll save it for next day. But it's just the Cartesian product of sets, and it just takes takes one set, here's the Coles notes. One set, you list all the elements here, and then another set, you list all your elements here, and then the combinations, right, in an XY type of pattern, those are your Cartesian product of sets, and it gives you more sets. So anyways, but we'll do that next day. And then we'll be done with chapter 2, and then we'll just move into chapter 12 after. Any questions before I let you go? No? So you've got that homework for all of chapter 2, and like I said, just the Cartesian product of sets is the only thing that we haven't touched on. But other than that, should be good to go. And I think it's not due till next Friday anyways. So you got time. Cool.
Technically, we'll only be able to finish up to halfway through 2.4 in the homework.
Yeah, most of 2.4 should be doable. I haven't looked at 2.4 specifically, so I don't know how many questions there are on the Cartesians, but yeah, you'll see. Maybe hold off on 2.4. Give yourself a break. Hey, what's going on there? There's 2 Niles. Anyways, if there aren't any questions, see you next week. Kick you guys all out. Peace.